6 machines begin a study together. 3 fail on day 2, day 4, and day 5. At the end of day 6, observation stops. The other 3 machines are still running. Their arrows do not hide known failure times. Each arrow says only that its lifetime exceeds 6 days.
Could we just record day 6 as their failure time?
No, that invents 3 failures. Deleting those rows is also wrong because it discards evidence that 3 machines survived at least 6 days. Censoring keeps the inequality without pretending to know the endpoint. The lifetime process is only one layer. The study design decides when observation stops, and that rule decides what a row can report. The complete generative story is called a data-generating process. The likelihood must score the record produced by that story, not the complete event we wish we had seen. Use a simple exponential lifetime model with rate parameter lambda. A larger rate means shorter lifetimes on average. Separately, the study design fixes an administrative cutoff at 6 days. The latent lifetime and the cutoff meet inside the observation rule. For each machine, record whichever comes first, failure or the cutoff. The displayed equation calls that recorded time the minimum of the two. Beside it, an event indicator is 1 for an observed failure and 0 when the cutoff arrives first. A lifetime of 8 days therefore enters the table as 6 days, censored.
So is day 6 another parameter to estimate?
Not here. It was fixed by the study schedule. With independent random censoring, separate censoring factors can also drop out of the relative likelihood for lambda. But the censoring indicator never becomes optional. It tells us which lifetime contribution each row requires. For an exact failure on day 4, the observation names an event time. Its likelihood contribution is the lifetime density evaluated there. Under this exponential model, that density is lambda times the exponential decay shown on screen.
Why not evaluate the density at day 6 for a censored machine?
Because no failure occurred there. Every lifetime beyond day 6 is compatible with the record. Add that whole tail and we obtain the survival probability, the chance of lasting beyond the cutoff. One compact expression now dispatches each row correctly. When the event indicator is 1, the density factor remains. When it is 0, the survival factor remains. Taking logs turns the product of 6 contributions into a sum. 3 observed failures supply 3 copies of the logarithm of lambda. All 6 machines contribute their time under observation. 2 plus 4 plus 5 plus 6 plus 6 plus 6, or 29 machine days. The result is 3 log lambda minus 29 lambda. First, pretend all 6 endpoints were failures. That incorrect likelihood counts 6 observed failures, so it favors a higher failure rate. Numerical maximization places the rate near 0.207 per day, corresponding to an estimated mean lifetime of only 4.8 days. Now restore the 3 censoring arrows. The correct likelihood has only 3 failure terms, while all 29 machine days remain. Its peak moves left. A numerical optimizer evaluates the curve and settles near rate 0.103 per day. The fitted survival curve lifts, and the estimated mean lifetime becomes about 9.7 days. The latent lifetime family did not change. The numerical optimizer did not change. Only the model for how lifetimes became recorded rows changed, and the fitted mean nearly doubled. That is why an observation mechanism is part of the statistical model, not clerical metadata added afterward. Right censoring reports a tail, but other instruments report other regions. If inspection happens only once a week, a failure may be known only to lie between 2 visits. Its contribution is the probability inside that interval, the cumulative probability at the upper limit minus the cumulative probability at the lower limit. Rounding and detection limits use the same idea. Truncated sampling is different. A censored machine leaves a partial row, a truncated machine never enters the table. If a study enrolls only machines that have already survived 2 days, the observed density must be conditioned on passing that entry gate. That conditioning denominator renormalizes the distribution among machines eligible to appear. Our 6-day cutoff was fixed in advance, so the simple survival contribution was justified. If struggling machines leave observation early, dropout and failure may be related. Then the censoring process carries information and needs a richer joint model. Finally, multiplying the 6 row contributions assumes the machines are conditionally independent under the model. The likelihood is determined not only by what can happen, but by what the experiment was capable of recording.